picking up good vibrations.
After this high-level motivation, let us move to a more concrete and mathematical motivation to consider convolution. Let us start with a very important fact that combines two facts we have seen previously. We know from previous lectures that we can write any discrete time signal as a weighted sum of delta direct signals. Moreover, we know that if the system is linear, when we apply as an input a weighted sum of function or signals, then the output response will be the sum of the individual responses to each of the signals. So if we know the output response to simple input signals, which are these delta directs shifted by different values, we can compute the output response to any input signal. Let us illustrate this with an example. If we have a linear system, and if we know the responses when we apply a direct at times 1, 2, and 3, then for any signal that only takes values, non-zero values, at times 1, 2, and 3, we can compute the overall response by multiplying the value of the input signal at time 1 by the impulse response at time 1, and doing the same at times 2 and 3, and then adding all these three signals. But it gets even more interesting. If additionally to linearity we also assume time invariance, we know that if we apply an impulse at time 0 and we get a given response, if we apply an impulse at time t0, we get the same response but shifted by t0. This means that all the signals h0 of n, h1 of n, h2 of n, corresponding to impulses at time 0, n equals 0, n equals 1, n equals 2, can be computed from a single h of n, which is nothing more than the impulse response of an impulse at time 0. And all these h0, h1, h2 will be shifted versions of this hn. So it will be h of n minus 0, h of n minus 1, h of n minus 2. So all we need is the impulse response to a direct at time 0, h of k, to determine all the other ones. The impulse response h of k, h of n, is all that we need to fully characterize a linear time invariant system. We can then write the output response to an LTI system to an arbitrary signal as y of n, the output, is equal to the summation from k equals minus infinity until infinity of x of k, h of n minus k. And this is nothing more than replacing the previous formula h of underscore k of n, which were the output responses to impulses at times k, by h of n minus k, because that is exactly the output response when to an impulse at time k when the system is linear time invariant. You do not have to memorize the order x of h, because as we will see, one of the properties of a convolution is that we can exchange the convolution between x and h is the same as the convolution between h and x. Now, the formula is slightly different when the two signals x and h only start at 0. In this case, we can replace the summation from k equals minus infinity until infinity by the summation from k equals 0 until infinity, because x of k is 0 for negative k. Moreover, since we can consider the summation, and we can also consider summation only until k equals n. And this is because for larger values of k, let's say n plus 1, n plus 2, when we replace them in h of n minus k, we obtain h of minus 1, h of minus 2, which is 0. So we are left with this simplified formula, with the summation from k equals 0 until n of xk, h of n minus k. Now, the fact that the impulse signal, the input signal is starts at 0 is nothing special, because we can make that convention. Also, the impulse response for causal systems must start at 0. It has to be negative for negative values. And this just simply follows from the fact that if we apply a pulse at time 0, we cannot have an output that starts before time 0. That would mean that somehow those values would have to guess, those values at, let's say, n minus 2 and minus 1, would have to guess there would be an impulse at time 0. So the impulse response for causal systems must be 0 for negative time, can only take non-negative values from n equals 0 onwards. Now, if we know the impulse response of an LTI system, we could follow the following procedure which we have already illustrated before. For each value where x is non-zero, and for this example it is for time 0 and 1, we simply multiply the shifted impulse responses by these values and then we add them. In this example, we multiply h of n by x of 0, which is 1, and then h of n minus 1 by x of 1, which is 1 as well. And then we add these two. However, this is generally quite hard. Just imagine you have to follow this for the new signal that shows up now in the slide. This would be very hard. So typically convolution is carried out with a different but of course equivalent procedure explained in the next video.